Hello again, everyone. Today we will be going over exponents. Exponents are written as smaller numbers or expressions to the top right of normal numbers or expressions. And they are also referred to as powers. The expression that the exponent is acting on is referred to as the base. As you might be aware, exponents tell us to multiply the base by itself equal to the number of times as the exponent. So 3 to the second power, or 3 squared, tells us to take 3 multiplied by itself twice. 3 times 3 will give us 9. Then 3 cubed, or 3 to the third power, is 3 times 3 times 3, which will be 27. Then 3 to the fourth power will be 3 times 3 times 3 times 3, which will end up giving us 81, and so on. So that gives us a nice understanding on some positive integer exponents, but what about some other cases like to the 0 power or to a negative power? Well, for anything to the 0 power, the rule is we just get back 1. So 3 to the 0 power is going to be 1. 100 to the 0 power will give 1. And 1 over 7 to the 0 power will just give 1. The only exception to this is 0 to the 0 power, which is undefined. Next, we want to understand what happens when we have a negative exponent. Let's say we have some number a raised to the negative n power. Well, a negative exponent simply tells us to take the reciprocal. In other words, this a, which is currently on the numerator, will be moved to the denominator by taking the negative in the exponent and turning it into a positive. So we get 1 over a to the now positive n power. Similarly, if we now have 1 over a to the negative n power, the a has a negative exponent in the denominator, and we can turn that into a positive exponent by bringing it to the numerator now, so we just end up getting a to the n. This is how we interpret negative exponents. Now that we understand some basics, let's delve into some more rules on exponents. If we have two expressions that are being multiplied together that have the same base a, but raised to some possibly different exponents, what this will end up being is just that base a now raised to the sum of the two exponents. This is the product rule, and to see how this works out, let's consider a to the second power multiplied by a to the third power. Well, if we took what we know about exponents and just wrote them out, a squared giving us a times a, and a cubed, a times a times a, counting up all these a's that are multiplying together, we get 1, 2, 3, 4, 5. So this is just 5 a's multiplied together, which is just a to the fifth power. Notice the 5 we ended up with is just the sum of the 2 and 3, the exponents from the left side, just like we expected. Now instead of multiplication, let's consider division. If we again have some number a as our base, raised to the n power, now divided by that same a raised to the n power, the quotient rule of exponents tells us that this will end up being a raised to the m minus n power. To see this, consider a to the fifth power divided by a squared. We know we can switch the sign on an exponent by moving between the numerator and denominator, so let's take the a squared that's in the bottom and move it to the numerator by switching it to a negative. By doing this, we've turned the division into multiplication, and we can use the product rule we just found out. The product rule will tell us to take the two exponents, 5 and minus 2, and just add them together. So we see that our new exponent for a is just the difference between the exponent from the numerator and the exponent from the denominator. In this case, we'll get a cubed. Now, what if we tried to raise something that already had an exponent to another exponent? If we add a to the m power, now raised to the n power, the power rule of exponents tells us that we'll just take the m and n and multiply them together for a new exponent. To see this, consider a squared raised to the third power. Using our base understanding for exponents, the cube on the outside just tells us to take the a squared multiplied by itself 3 times. And we could write out each of these a squareds as a times a, and we see that we have 1, 2, 3, 4, 5, 6 a's all multiplied together, which will give us a to the 6th power. This 6 is the same as if I had multiplied the original 2 and 3 exponents together. So we've now seen how the product rule, quotient rule, and power rule all work for exponents. Lastly, let's consider how exponents distribute into more complex expressions. Simply put, exponents will distribute across multiplication and division, but not across addition and subtraction. For multiplication, if we had two numbers, a times b, then raised to some exponent n, the exponent n can distribute into each term being multiplied. This will give us a to the n multiplied by b to the n. For an example, let's consider 2 squared multiplied by 3, then raised to the third power. We will evaluate this two different ways. First, using our order of operations, which we know will give us the correct answer, and then using the distribution of the exponent. Our order of operations will tell us to evaluate the inside of the parentheses first. So 2 squared will be 4, then multiplied by 3. We get 12 on the inside, raised to the third power, and 12 cubed will give us 1,728. Now distributing the exponent, we will have 2 squared raised to the third power multiplied by 3 to the third power. Using our power rule of exponents, the 2 and 3 here will multiply together to give us a new exponent of 6. Still multiplied by 3 cubed. 2 to the 6 will end up giving us 64, while 3 cubed will be 27. Multiplying these two together will again give 1,728. These answers match, so our distribution of exponents works across multiplication. For division, if we now have a divided by b raised to the n power, the exponent n will distribute to each term in the division. This will end up giving us a to the n power divided by b to the n power. To demonstrate this, consider 2 cubed divided by 4 raised to the second power. Again, we'll evaluate this two different ways. First, using our order of operations, evaluating the inside of the parentheses first. Doing the exponent inside first, the 2 cubed will give us 8, still divided by 4 and raised to the second power. Doing the division inside, 8 divided by 4 will give 2 squared. 2 squared will just be 4. Now if we distribute the exponent, we will have 2 cubed to the second power on top and 4 squared on the bottom. Using our power rule again, the 3 and 2 will multiply together, giving us 2 to the 6th on top, still divided by 4 squared. 2 to the 6th will give us 64, and 4 squared will be 16. Doing this division will give us 4 again. These answers match, verifying that our exponent distributes into division. To show that exponents do not distribute into addition or subtraction, consider now 2 plus 3 squared and compare it to 2 squared plus 3 squared. Evaluating the one with parentheses first, we'll have the addition inside the parentheses. 2 plus 3 is 5 squared. 5 squared will give us 25. But now if each of them is getting squared, 2 squared is 4, plus 3 squared is 9. Doing this addition will give us 13. These numbers do not match, which tells us we cannot simply distribute the square into each number in the sum. And so we have discussed most of the aspects of exponents, which you can see here. We could also relate fractional exponents to radicals or roots, but we will save that for when we discuss radicals in depth next time. Until then.